I wanted to take a slight detour in my I wanted to take a slight detour in my fluid mechanics video series, just to go over some of the other calculus-based things we'll be talking about, such as stress and pressure fields, looking with a more rigorous approach and things like that. As I said before, this will be have some calculus to it, and actually some partial differentials at that. Essentially, we'll go over a quick review. We have the integral of x squared dx, and that's just obviously we know is 2x. And then, the reverse of that's also true. It's just, again, it's like the antiderivative and derivative. It really makes perfect sense. Any of you guys have studied calculus, this is probably just a review, just a somewhat of a redundant review. But I just figured it's important to go over a few things that I'll be discussing. So we have things such as gradients, which is a vector operator, and we're going to be talking about gradients and pressure fields, and it's just some vector calculus will be discussed. We'll talk about the gradient first in this video, and I'll talk more about the curl, divergence and curl, and so a few other vector calculus theorems, such as Green's theorem, things like that, and then we'll move back to the actual, physics of fluid mechanics. Essentially, we have the partial derivative in the x direction for the I direction, and then we have the partial derivative with respect to y in the j direction, and that's defined in R2, or two-dimensional real space. And let me just move this down a little bit, but this can be generalized actually to the gradient operator being defined, partial derivative of x, partial derivative of y, dot partial derivative of n. So if that can be applied to n dimensions. Take a partial derivative of n dimension, you'll be able to find the gradient. And essentially, you're finding n r to the n plus 1. You're trying to find like the slope in the z direction for R2, or well, it's kind of R3, because you're trying to find which direction will you go to get the maximum slope in the z direction, and things like that. It's essentially what the gradients is discussing. Then we have stuff like divergence and curl, which we'll talk about more in the next one. But essentially, going forward, we'll talk again pressure fields, gases, ideal gas laws. Have a few examples of that. Maybe a few fluid mechanics derivations. Then I'll talk about how fluid mechanics is applied to aerospace engineering. We'll talk about fluids around plane wings. We'll talk about propulsion systems, things like that. I guess it'll be kind of fluid mechanics plus a little bit of applications of it. But this will probably be a pretty relatively long video series, but nonetheless it'll be informative. And if you guys like fluid mechanics, there's a lot of information, and as I said in my previous videos, it's very widely applicable, especially to aerospace engineering. So I guess for a review, again, we'll talk about integrals, we'll talk about derivatives, we'll talk about the gradients, we'll talk about then we'll do double integrals. Essentially, this will be like a quick review of calculus, and then we'll just move into the actual fluid statics and fluid dynamics video. So hope you guys enjoyed. Just brush up on calculus if you're a little rusty, and I guess the next couple of videos we'll talk about I guess Newtonian fields, stress tensors, and then we'll start applying some calculus to fluid mechanics and like a rigorous approach to it, and we'll kind of revisit some of the stuff we talked about and apply calculus to it. All right, thanks for watching. See you guys later.